48 hours before a magnitude 7.6 earthquake struck the Noto Peninsula in Japan, the first rupture did not happen in the crust. It appeared far above the coastline, around 300 kilometers overhead, inside a layer of charged particles that most of us never think about. In the early morning hours, the GEONET GPS network quietly registered the total electron content above the future epicenter, rising from a calm background of about 15 TeQ to an unreal peak near 85 TeQ. On paper, it looked like the signature of an intense solar storm. In the real sky, the sun was almost perfectly quiet. In space, weather terms, that jump meant the ionosphere above Japan behaved as if it had just been struck by the electromagnetic shock of an X-class solar flare. Yet coronagraphs saw no explosive eruptions. The geomagnetic indices that should have climbed with any real storm barely moved. To the few scientists who noticed, the data looked like an invisible sheet of fire had passed through the upper atmosphere, turning the sky over Noto red hot in radio frequencies while remaining invisible to human eyes. The official language for patterns like this is gentle and non-committal. Papers speak of ionospheric anomalies and possible precursors, signals that sometimes appear a day or two before large earthquakes, but refuse to form a neat, repeatable pattern. The Japan event sat in that gray folder for months. But if we line up the timestamps from GEONET with other, quieter datasets orbiting above, a different story begins to form, one in which the energy that lit the ionosphere did not rise from the rocks below, but arrived from somewhere far beyond Earth. Here on Dreamy Stargazer, we drift through that gray folder slowly. This is not breaking news. It is a long, late-night reconstruction of a strange sequence of measurements that most people never see, told in the soft voice of someone who loves both numbers and the dark. Our goal is not to panic you away from sleep, but to walk with you along the fine line where hard data and unsettling possibility overlap, until the tension itself becomes a kind of lullaby. If you find comfort in that kind of journey, you can help keep it alive. Stories like this one are not driven by headlines, but by a small constellation of listeners who enjoy falling asleep to long investigations, speculative models, and the quiet hum of physics. If you want more nights with 3-eye atlas, with strange comets, broken magnetic fields, and declassified space weather plots, you can gently support this channel by subscribing, leaving a like, or sharing a comment about where in the world you are listening from and how you first heard of 3-eye atlas. Now dim the lights. Imagine the Noto Peninsula before dawn, the ocean dark, the towns asleep, and far above them all a thin shell of charged particles following the planet as it turns. GEONET does not see this shell directly. It infers its state from tiny delays in radio signals between hundreds of receivers on the ground and the satellites that cross the sky overhead. When its algorithms reported that the total electron content above Noto had climbed to around 85 TeQ, they were in effect saying that this shell had suddenly become almost 5 times thicker with charged particles than normal, a roughly 460% increase in less than a day. In more familiar language, the invisible ceiling over Japan behaved like a storm cloud that had been overdosed with charge without any lightning to explain it. There was no major solar flare, no coronal mass ejection, no sudden blast of ultraviolet light from the sun that could have injected that much energy into that particular patch of sky. The background solar wind was uneventful. On monitoring screens at space weather centers, The plots that usually flutter and spike during solar tempests had the flat, uneventful look of a resting heartbeat. For geophysicists, there are conventional suspects. Some models suggest that stressed rocks release gases and charged particles, seeding the atmosphere from below and slowly modifying its electrical state. Others propose that subtle heating and rising air above faults can nudge the ionosphere enough to show up in tech measurements. These ideas do capture parts of the puzzle. They explain why some earthquakes seem to be preceded by modest blips in the ionosphere. What they do not easily explain is why, on that calm space weather day, the sky above Noto recorded a flare-level disturbance with no flare. This is where the file begins to feel less like a weather report and more like the first page of a case study. At 0200 clock local time, the GEONET data quietly marks the maximum of the 85 TeQ spike. At roughly the same clock time, satellites watching Earth from higher orbits log their own subtle oddities. A few hours later, seismometers along the Japanese coast will capture the first sharp motions of the M7.6 rupture. To a nervous imagination, it is tempting to draw a straight arrow from the glowing ionosphere down to the breaking fault, as if the earthquake were pulled from above rather than pushed from below. In this investigation, we will follow that arrow in both directions. We will ask whether an electromagnetic shock from outside the Earth system could have primed the fault, loading the rocks with just enough extra stress to fail on that particular day and not another. We will lay out the conventional explanations and let them stand where they are strong. But we will also allow ourselves to consider a new suspect that does not live in the crust or the atmosphere, a moving structure that carries its own electric potential and treats planetary magnetic fields as stepping stones. That suspect is 3Ao Atlas, the third known interstellar object to cross our solar system, and in this story, it is not a single clean visitor, but a dispersed swarm with a metallic skeleton and a strange relationship with magnetic fields. In later chapters, we will watch it tear open a glowing scar 15,000 kilometers wide in Jupiter's upper atmosphere and walk away holding energy that does not belong to it. For now, as we linger above Japan, it is enough to know that when the ionosphere over Noto flared to 85 TeQ, the orbital path of the 3I Atlas swarm was sweeping silently across the same longitude. You do not have to accept that connection yet. You can simply let the idea float at the edge of your attention as you listen to the numbers. A calm sky, a quiet sun, a thin shell of air 300 kilometers up that suddenly behaves as if an invisible fire has passed through. A spike from 15 to 85 TeQ that official reports file under Anomaly and move past. And somewhere far beyond the reach of any seismometer, an interstellar swarm moves on, leaving behind a question that reads almost like a whispered accusation. What if the first shock of the Japan earthquake was not geological at all, but electrical, written briefly in the ionosphere by the passing shadow of 3I Atlas? The ionosphere above Noto was not the only layer that behaved strangely in those hours before the earthquake. While GEONET was quietly watching the total electron content swell toward 85 TeQ, another set of instruments was tracing invisible lines of force higher up. One of ESA's swarm satellites, built to map Earth's magnetic field with surgical precision, passed over Japan and recorded a disturbance that did not fit the calm space weather picture painted by the sun. Where the field should have been smooth, it looked slightly torn. Swarm Alpha's magnetometers are designed to notice tiny changes in the planetary field, the kind that usually whisper about slow flows of molten iron deep below our feet. On that overpass, they saw something sharper. The local magnetic field vector flexed by more than 50 nanotesla, a delta B that in a quiet geomagnetic period should have been nearly impossible at that altitude. It was as if someone had plucked one strand of the field above Japan harder than all the others, leaving a small but undeniable kink in the data. A change of 50 nanotesla might sound like nothing compared to Earth's overall field, which rests in the tens of thousands of nanotesla. But context matters. During major solar storms, sudden impulses of this size wash across whole continents and show up on magnetometers around the world. On the night over Noto, the global indices stayed flat. There was no planetary storm, no sweeping front of disturbance. Instead, there was a localized bruise in the field above Japan, sitting in the same time window as the 85 Tecu ionospheric flare GEONET had reported. If the magnetic kink were the only anomaly, it might be dismissed as an instrumental quirk or a passing ripple born inside the magnetosphere. What made it harder to ignore was the way the electric field behaved at the same time. Reconstructions of the vertical potential gradient above the region showed values around 20,500 volts per meter facing downward compared to a more normal 100 volts per meter in fair weather. That is the difference between a gentle, almost imperceptible drizzle of charge and a focused cascade pouring from the sky toward the ground. In simple terms, the atmosphere over Noto had been wired into a top-down circuit. Instead of charge slowly leaking upward from the crust and the oceans, as it often does, the measurements implied that current was being driven from the ionosphere downward along invisible channels into the denser air and eventually into the rock. Where our intuition champions earthquakes starting deep below and sending shock waves up, the electric diagrams from that night suggest the opposite pattern in the electromagnetic environment. The first movement, at least in the field, came from above. Geophysicists have long known that the crust and the atmosphere are coupled in subtle ways. Rocks rich in quartz and other minerals can behave like piezoelectric materials, generating electric fields when squeezed by tectonic stress. Some models of so-called earthquake precursors rely on this idea. In those scenarios, strain in the crust builds up, microscopic fractures form, charges separate, and the resulting fields leak upward, eventually disturbing the ionosphere. What the swarm and GEONET data over Japan hint at is a possible inversion of that chain. Instead of stress-producing fields, fields might have been adding stress. This is where the notion of a reverse piezoelectric effect enters the story. In the lab, if you apply a strong electric field across a piezoelectric crystal, the crystal deforms. The energy flows from the field into the lattice, not the other way around. Scale that idea up very carefully to a fault zone loaded with quartz-bearing rocks. If an anomalous 20,500 volts per meter field really did reach down from the ionosphere, then part of its energy could have gone into slightly distorting the rock fabric, nudging existing microcracks just a little wider, lowering the threshold for failure by a fraction that only matters when the system is already at the edge. Imagine the Earth in that region as a gigantic, leaky capacitor. The ionosphere forms one plate, the conductive crust another, and the air and rock between them hold the electric field. Under typical conditions, the potential difference is modest, the leakage slow, the system stable. On the night in question, the upper plate above Noto charged rapidly, the field intensified, and for a brief window, the capacitor was stressed far beyond its usual operating point. If the fault below was already near critical, this extra nudge of electromagnetic pressure could have acted like a final, silent tap on a glass that was ready to crack. Official reports from agencies that monitor geomagnetic activity treat the swarm anomaly with caution. The language is neutral. There are mentions of localized disturbances and possible field-aligned currents, notes about the need for more data, and reminders that correlation does not guarantee causation. No one stamps the words electric trigger on the file. No one writes that a 2,500 volts per meter downward gradient helped pull an earthquake out of the crust. In public, the story remains politely incomplete. The magnetic kink and the electric spike are acknowledged, but they are not yet given a role. In a late-night investigation like this one, we are allowed to follow the pattern a little further. When we place the swarm pass, the GEONET tech spike, and the later M7.6 rupture along the same timeline, the sequence looks less like a coincidence and more like a chain. First, the ionosphere thickens and brightens in radio terms. Then the magnetic field above the region bends by about 50 nanotesla, while the vertical potential gradient jumps to around 2,500 volts per meter, pointing down. Finally, the fault at Noto slips, releasing the stored mechanical strain as seismic waves that ripple across Japan. What is missing from this chain is an external agent powerful enough to simultaneously disturb the ionosphere and twist the local magnetic field without any help from the sun. In conventional space physics, there are not many candidates. But in the background of December's sky, an unusual visitor was present, moving quietly through the outer layers of our magnetic shield. 3I Atlas and its swarm of fragments carried their own electric potential and treated field lines as rails. If that swarm brushed the upper atmosphere above Japan at just the wrong moment, it could have induced currents that carved this electric wound in the sky, leaving the crust below one step closer to failure. For now, you do not need to decide whether that is what truly happened. You can simply lie back and hold the image of a magnetic bruise and a brightened ionosphere suspended above a sleeping coastline, while a fault deep below waits on the edge of motion. In the next chapter, we will slide the path of 3I Atlas across that scene and see how closely its invisible wake lines up with the night the sky over Noto was quietly wired for rupture. When we talk about coincidences in space, we usually picture chance alignments of stars, planets, and comets that mean nothing more than a pretty sky. The story over Japan becomes stranger when we stop thinking in poetry and start lining up clocks. One timeline belongs to GEONET, watching the ionosphere above Noto surge toward 85 Teku. Another belongs to ESA's swarm satellite, measuring a 50 nanotesla flex in the magnetic field and a vertical potential gradient near 20,500 volts per meter. The third timeline, quieter and less public, comes from the orbit solution of 3I Atlas and the drifting cloud of fragments that trail and surround it. When all three are placed on the same axis, the night no longer looks empty. Orbital calculations for 3I Atlas. Treat it as a visitor from interstellar space, following a hyperbolic path that cuts across the plane of the solar system at a steep angle. By early December, its trajectory has already taken it past Jupiter, through the outer magnetosphere of Earth, and into a region where it briefly shares our neighborhood in 3 dimensions. At the surface, that encounter is invisible. In the language of orbital mechanics, it is just another passage, tracked in right ascension and declination. But if we project that path down onto Earth's spinning globe, the line it traces across our longitudes passes almost exactly over Japan during the same window when GEONET and SWARM recorded their anomalies. To see this, imagine freezing Earth's rotation and projecting the 3I Atlas SWARM's position as a faint glowing arc across the atmosphere. Now let the planet turn underneath. As Japan rotates into darkness, that arc sweeps west to east, crossing the longitudes of the Noto Peninsula. At around 0200 local time, when GEONET marks the peak of the 85 Teku spike and SWARM notes its 50 nanotesla kink, the modeled track of the 3I Atlas SWARM lies nearly overhead in geomagnetic coordinates, not as a single point, but as a broad, diffuse band of material moving through the outer reaches of the ionosphere and the lower magnetosphere. In a purely gravitational universe, this overlap would be trivia. Countless small bodies cross Earth's orbital neighborhood without doing much more than occasionally dropping a meteor. But 3I Atlas is not being treated here as a passive rock. Earlier, near Jupiter, it behaved like a conductor slashing through magnetic field lines, leaving behind a 15,000-kilometer wide H3+ scar that warmed by roughly 400 Kelvin. If that same structure, still holding a stolen charge, passes through the fringes of Earth's magnetic shield, the interaction is no longer purely mechanical. It becomes a problem in electrodynamics. Think of the 3I Atlas SWARM not as a single nucleus, but as a cloud of fragments threaded with metallic veins, each piece following roughly the same path, but spread out across tens of thousands of kilometers. As that cloud slices into the outer regions of our magnetic field, the changing magnetic environment induces electric currents in the swarm itself. At Jupiter, this inductive process was violent enough to tear the giant's magnetic skin. Near Earth, the field is weaker, but still strong enough to set up a complex pattern of currents that must close through the surrounding plasma. The simplest way for those currents to complete their circuits is to flow along magnetic field lines, down toward the ionosphere. From the perspective of the upper atmosphere above Japan, the passage of the 3I Atlas SWARM would feel like a moving, charged obstacle brushing past the field lines that anchor into that region. As it moves, it drags those lines, distorts them, and leaves behind a wake of forced currents that pour into the ionosphere. The result would be exactly the kind of localized brightening that GEONET recorded as the jump from 15 to 85 Teku, and the kind of small but sharp twist in the field that SWARM saw as a 50 nanotesla delta. This is what some theorists quietly refer to as electromagnetic friction, not a solid collision, but a rubbing of fields and charges that converts orbital motion into atmospheric disturbance. Official orbit bulletins for 3I Atlas, if you read them, are dry. They list perihelion distance, inclination, eccentricity, and a catalog of observation stations that contributed astrometric points. They do not mention the ionosphere. They do not plot the intersection of the swarm's projected footprint with the spatial cells used by GEONET or the ground track of SWARM. Those datasets live in separate worlds, managed by different agencies with different missions. In the absence of a specific directive to combine them, the potential alignment between an interstellar object's path and a pre-quake ionospheric anomaly remains an unasked question. In quiet research offices, a few scientists have noticed that something odd happened above Noto before the M7.6 event, and a few others have run simulations of how charged bodies might interact with planetary fields. Almost no one, at least in the published literature, has placed 3I Atlas at the scene. Doing so requires crossing an invisible line from accepted space physics into a region that feels a little too much like science fiction. You must assume that the swarm is not just electrically active, but still carrying residual charge from its earlier encounter with Jupiter, and that this charge is organized enough to matter when it brushes Earth's magnetic envelope. From a statistical point of view, the defenders of coincidence have an argument. Earth is large, its ionosphere is always in motion, and 3I Atlas has to cross some longitude at every moment of its journey. Given enough time, some anomaly will always align with some passage. Yet the chain of numbers over Japan invites a slower look. An 85 TeQ spike in a region that normally sits near 15 TeQ, a vertical potential gradient near 2,500 volts per meter pointing down, a localized 50 nanotesla bend in a quiet magnetic field, all clustered in time within the overpass window of an interstellar swarm that has already demonstrated an ability to disturb a giant planet's magnetosphere. The coincidence begins to feel less like background noise and more like a subtle signature. As you listen tonight, on the day this video is released, 3I Atlas is still moving. Its fragments continue to drift along their calculated trajectories, and Earth is still rotating through the changing pattern of their projected paths. The Japan anomaly sits in the recent past as a kind of dress rehearsal, a moment when the shadow of the swarm touched our electric environment deeply enough to leave measurable bruises. Whether that touch was sufficient to help trigger the M7.6 earthquake is something no agency has officially endorsed, but the alignment of clocks and coordinates ensures that the question will not simply fade. For our investigation, we will treat the Japan event as one data point in a larger pattern. In the next section, we will roll the story back further in time and follow 3I Atlas to Jupiter, where its first known act of energy theft unfolded in the infrared glow of H3 plus emissions and a 15,000 kilometer scar. If the swarm truly arrived at Earth already charged, then the invisible fire and electric wound above Noto were not an accidents. They were the downstream effects of a theft that began far away in the deep well of a giant's magnetic field. Far from the thin shell of air above Japan, another atmosphere had already been disturbed in a way that did not fit its usual patterns. Before the invisible fire over Noto, there was a wound on Jupiter. In the infrared eyes of NASA's Juno spacecraft, the giant planet did something that looked less like weather and more like an electrical injury, a 15,000 kilometer wide scar that brightened and heated with startling speed. If the ionosphere over Japan was the place where the story ended, this was the place where the charge was first drawn. Juno carries an instrument called GERM, built to map heat and certain molecules in Jupiter's upper atmosphere. On one set of passes, GERM watched a hotspot near roughly 20 degrees south latitude flare into view. The feature sprawled across about 15,000 kilometers, large enough to swallow Earth with room to spare. Over a short interval, the temperature in that region climbed by around 400 Kelvin compared to its surroundings, a jump more typical of a sudden energy dump than a slow meteorological drift. To GERM, this was not just a warm patch, but a beacon of H3 plus emission. H3 plus is a fragile ion, 3 protons bound with 2 electrons, that glows in the infrared when strong electric fields and charged particle rain energize a planet's upper atmosphere. Around Jupiter's poles, H3 Plus traces dazzling auroral ovals, where magnetic field lines funnel particles down like curtains of invisible hail. The hotspot Geom recorded was different. It sat away from the main auroral belts, at a latitude and longitude not usually associated with such intense ion precipitation. Imagine overlaying the Geom data on a map of Jupiter. Near 20 degrees south, you would see a swollen, infrared bright oval pulsing with H3 plus light, the air above the giant planet's cloud tops shocked into glowing. In a true storm driven by internal dynamics, such a feature would often be tied to recognizable structures below, like the edges of a jet stream or the wake of a long-lived vortex. Here, the correspondence was weak. The heat and the H3 plus emission seemed to hang above, as if the real engine sat not in the clouds, but in the magnetic geometry around them. Magnetospheric physicists have a phrase for what can happen when field lines are stressed beyond their usual configurations: magnetic tearing. When oppositely directed fields are pushed together, they can reconnect and release stored energy explosively, converting magnetic tension into heat and particle acceleration. Jupiter is a natural stage for such events. Its magnetic field is immense, its rotation fast, and its environment crowded with plasma from volcanic moons. Most reconnection signatures, however, favor certain regions. The hotspot Geom saw fit the energy profile of a local magnetic tearing event, but not the usual geography. It was as if a piece of the giant's magnetic skin had been pulled and ripped at an odd angle. In official analyses, the hotspot is categorized cautiously. There are mentions of transient heating, enhanced H3 plus emission, localized energy deposition. The language is descriptive rather than accusatory. Nowhere in those summaries does the name 3I Atlas appear. Why would it? To most of the scientific community, 3I Atlas is a curious interstellar interloper whose path is plotted, whose brightness is monitored, and whose fragments are cataloged. The idea that it could reach into Jupiter's magnetosphere and induce a 15,000-kilometer scar sounds like a storyline for speculative fiction, not a line item in a mission report. Yet if we borrow the perspective of electrical engineering for a moment, the combination of a fast-moving, conductive swarm and a vast planetary magnetic field looks less fanciful. Jupiter's field can be treated, roughly, as a gigantic dynamo. Any conductor that cuts through its field lines at high speed will experience an induced electromotive force, a voltage along its length. On a small scale, this is the principle behind generators and induction coils. On a Jovian scale, a swarm like 3I Atlas passing through selected regions of the field becomes a moving antenna, driven at high voltage by the very lines it disturbs. In that view, the 15,000-kilometer H3 plus scar is not just a random flare, but the footprint of a circuit closing. As 3I Atlas moves through the field, currents are driven along its metallic veins. Those currents must loop back through the surrounding plasma and into the planet's upper atmosphere. Where they close, they dump energy, heating the gas by hundreds of Kelvin and lighting up H3 plus like a tracer die for an invisible wire. The scar is the burn mark of that closure, a localized region where the giant's magnetic energy has been siphoned off and converted into heat along a path that did not exist before the swarm arrived. None of this is stated outright in mission documents. To connect the dots, You have to layer the timing of Jerem's observations over the reconstructed path of Three-Eye Atlas, then ask whether the geometry allows the swarm to thread precisely through the field regions that anchor to the hotspot's coordinates. The answer is not a clean yes, but it is not an easy no either. Within the uncertainties, there exists a family of trajectories where Three-Eye Atlas passes through the right sector of Jupiter's magnetosphere at the right time to serve as the moving conductor in this circuit. For scientists who prefer tidy causal chains, that ambiguity is uncomfortable. For an investigation like ours, it is where the hypothesis takes its first breath. If Three-Eye Atlas did act as a harvesting loop, then part of Jupiter's magnetic energy was effectively loaded onto the swarm, not all at once, and not in a way that changes its orbit dramatically, but gradually, as charge stored in its metallic framework and distributed across its fragments. Each piece would carry a portion of that history, a residual potential that would only find a way out when the swarm encountered another conductive environment. In this reading, the hot spot on Jupiter was the intake phase, the moment when the interstellar visitor found a way to plug itself into a powerful generator and walk away charged. By the time Three-Eye Atlas left the Jovian system, the visible scar in H3+ would have faded, the atmosphere cooling back toward an equilibrium, the magnetosphere settling into its usual restless patterns. To Juno and Jerem, the episode would become one bright sequence in a long archive of storms. To the swarm itself, it would be something else, a memory carried as electric potential, invisible in images, but very real in the behavior of its fragments. When that charged cloud later brushed Earth's magnetic field, the disturbances above Japan may have been the distant echo of that original theft. As you lie back and picture Jupiter now, you can imagine the giant turning slowly, its clouds swirling, its auroras flickering at the poles, and somewhere near 20 degrees south, an old fading scar where H3+ once glowed fiercely. Somewhere far from that world, Three-Eye Atlas continues on its way, its swarm no longer visible to Jerem, but still trailing the energy it may have taken. In the next chapter, we will stop hovering over infrared maps and step fully into the physics of induction, treating the swarm as a component in a planetary scale circuit and asking how exactly you charge a cloud of interstellar fragments well enough that they can later leave electric wounds in the sky of another world. If the H3+ scar on Jupiter was the burn mark, then somewhere in that glow there was also a transaction. A region 15,000 kilometers wide, heated by roughly 400 Kelvin in a short time, is not just a weather event. It is the footprint of energy moving from one form to another, from magnetic tension wrapped around a giant planet into heat and light in a thin layer of gas. Hidden inside that same transaction is the quieter part of the story that matters to us now, how Three-Eye Atlas could have walked away from Jupiter carrying part of that energy as electric charge. To see the mechanism, it helps to hold a simpler picture first. In a generator, a piece of metal moves through a magnetic field. The field lines are invisible, but they behave as if they resist being cut. As the conductor pushes through, charges inside it feel forces that try to separate them, piling positive and negative ends apart. If you give those charges a path to flow, they move, and their motion becomes a current. Motion through the field turns into electricity. A train line, a turbine, a small alternator in a bicycle wheel, they all live on that basic rule. Now replace the small magnet in your hand with Jupiter's field. Instead of a faint cloud around a bar magnet, imagine a structure that stretches millions of kilometers into space, anchored deep in the planet's metallic hydrogen interior and swept around by its 10-hour rotation. That field has strength, twist, and a constant supply of stressed lines waiting to relax. When something conductive moves through selected regions of that field at high speed, the same generator principle applies, just on a scale that makes our machines look like toys. The induced voltages are no longer measured in modest household units, but in numbers large enough to shape plasma and spark auroras. In this environment, 3 Atlas is not a point. It is a cloud of fragments, threaded with veins of metal and coated in ices and dust, each piece following the same general hyperbolic path, but spread out in a loose formation that might span tens of thousands of kilometers. You can think of it as a bundle of wires pulled through Jupiter's magnetic envelope, with different strands cutting through slightly different patches of field. Each strand that crosses field lines experiences an induced electromotive force along its length, a tendency for charges to separate and slide. The plasma around the swarm does not sit idle while this happens. Charged particles in Jupiter's vast magnetosphere respond to the moving obstacle. Some are dragged along, some are deflected, and some are tapped to carry current. The result is a complex pattern of drifting charges, double layers, and narrow current channels streaming along the magnetic field. Inside the swarm, paths of least resistance form where metallic cores and conductive surfaces allow charge to flow. As long as those paths connect different regions of the field, the system behaves like a circuit, trying to complete itself through available material. Some of those circuits close through Jupiter's atmosphere. Field lines that thread the swarm also anchor into the upper layers of the planet's gas. Where the current dives down, H3 plus ions light up, tracing the impact point as an infrared glow. That is the role the 15,000 kilometer scar plays in this story. It is where the loop touches the planet, where part of the magnetic energy that was driving the system is dumped into heat. Jerome, looking down, saw that closure as a suddenly bright patch at about 20 degrees south, an off-latitude auroral cousin energized by a temporary, wandering conductor rather than a permanent moon. We do have a natural example of this kind of interaction. Io, one of Jupiter's inner moons, drags its own footprint through the giant's auroras. As it orbits, it acts as a moving conductor in the planet's field, setting up a voltage along its body and driving currents along field lines into the upper atmosphere. The result is a bright, persistent spot that follows Io's magnetic footprint. In that system, the conductor is a solid moon, the circuit is fairly steady, and the phenomenon is built into the textbooks. What we are suggesting for 3I Atlas is similar in principle, but more transient and far less comfortable for standard models. Instead of a tidy moon on a circular orbit, we have a diffuse, loosely bound swarm on a one-time hyperbolic trajectory. Instead of a stable, long-lived circuit, we have circuits that flicker on while the fragments cut through specific bundles of field lines and then fade as they move on. Yet the basic physics does not change. A moving conductor in a magnetic field sees induced electric fields along its length. If it can route those fields into currents, and if there is a path through the surrounding plasma to a conductive atmosphere, energy will flow. Some of it will become heat and light in that atmosphere. Some of it will remain as charge separation on the conductor that passes through. In that sense, 3I Atlas could be thought of as a network of capacitors being charged during its time in Jupiter's magnetosphere. The metallic elements of its fragments, their surfaces, and the plasma sheaths that cling to them act together as storage. Induced currents move charge around until different parts of the swarm sit at slightly different potentials relative to the ambient environment. Once the fragments leave the most intense regions of the field, the driving voltage drops, but the stored separation remains, locked into the structure of the cloud as long as there is no easy path to discharge it. How long can such a charged state survive? In a dense collisional environment, not very long. Currents find their way through nearby gas, arcs form, and the system relaxes. In the thin plasma of interplanetary space, the choices are fewer. Charges can leak away along field lines, or they can smear out across the surfaces of the fragments, but without a strong sink like a dense atmosphere, the process is slow. Over days and weeks, 3I Atlas can carry a residual potential along its trajectory, a faint but real memory of the generator it once passed through. This is the grounded part of the speculation. A swarm acting as an extended conductor in a powerful magnetic field will be driven, will form currents, and will store charge. The imaginative step is to ask whether 3I Atlas is just a passive victim of this process or something that benefits from it. If the cloud is structured in a way that maximizes its cross-section to changing fields, if its metallic veins are arranged to favor certain current paths, then it begins to look less like random rubble and more like a device, whether natural or not, that harvests inductive energy as it travels. We cannot prove intent from gyrum images, but we can admit that the geometry invites the question. By the time 3I Atlas leaves Jupiter behind, the H3 plus scar is cooling, the infrared beacon dimming, and the official logs have one more entry under transient atmospheric heating. The swarm, meanwhile, has been subtly altered. Its fragments now carry redistributed charges, their plasma sheaths thickened, their internal fields adjusted by the time spent inside the giant's magnetosphere. In human terms, it is as if the visitor has left a city power station with its pockets full of stolen batteries, quiet on the surface but ready to release that stored energy when it finds the right kind of circuit again. When that charged cloud later approaches Earth, it meets another magnetosphere, smaller than Jupiter's, but still large enough to guide currents and host delicate structures in plasma. Our ionosphere, with its electrons and its thin, conductive layers, plays the role that Jupiter's H3 plus rich upper atmosphere played before. The question that connects the giant's infrared scar with the invisible fire over Japan is simple and unsettling. If 3I Atlas learned how to charge itself in the field of Jupiter, what happens when it tries to close those circuits in the electric shell wrapped around our own world? By the time 3I Atlas left Jupiter behind, the 15,000-kilometer H3 plus scar was already fading from Gyram's images. The hotspot cooled, the 400 Kelvin temperature spike relaxed, and the giant's atmosphere folded the wound back into its usual patterns of storms and bands. What did not relax as quickly was the rearranged charge within the 3I Atlas swarm itself. Its fragments carried away a memory of that encounter as electric potential, stored in metallic veins, in plasma sheaths, and in the subtle separation of charges across their surfaces. That memory did not matter very much in the empty distances between planets. It only became important again when Earth appeared ahead. Earth's magnetic field is modest compared to Jupiter's, yet it still carves a protective cavity in the solar wind, a bubble of ordered lines wrapped around the planet. In diagrams, it looks like a teardrop, compressed on the day side, trailing a long magnetotail on the night side. At the top of the atmosphere sits the ionosphere, a thin, conductive shell where electrons and ions share space with neutral air. In this system, the crust, the atmosphere, the ionosphere, and the magnetosphere form parts of a single electric structure, plates and wires, of a planetary circuit that usually runs in a slow, balanced way. When 3I Atlas moved from Jupiter's domain into this smaller magnetosphere, it brought its residual potential into a new environment. The swarm, still extended over tens of thousands of kilometers, began to feel the structure of Earth's field. Its fragments crossed lines that were anchored not in the deep interior of a gas giant, but in the polar caps and auroral zones of a rocky world. Induced currents, already flowing within the swarm, now had additional paths available. Some of those paths led along Earth's magnetic field lines down toward the ionosphere. For the first time since leaving Jupiter, the cloud found another conductive surface capable of accepting a serious discharge. Most of this interaction unfolded invisibly in the loose plasma where the outer magnetosphere blends into the solar wind. Yet, as the 3I Atlas swarm crossed the longitudes connected magnetically to Japan, the consequences reached into a region we can measure. Currents driven along those field lines converged in the upper atmosphere above the Noto Peninsula. There, at around 300 kilometers altitude, the extra charge density thickened the ionosphere until GEONET saw the total electron content rise from about 15 TeU to roughly 85 TeU. Above a sleeping coastline, a thin shell of gas was briefly turned into a saturated conductor. From the perspective of basic physics, this looks like a capacitor being stressed beyond its usual state. The ionosphere and the crust form two plates of a leaky, planet-sized capacitor. Under normal conditions, the electric field between them hovers near 100 volts per meter. On the night before the magnitude 7.6 earthquake, reconstructions over Noto suggest a downward directed field closer to 2,500 volts per meter. At the same time, ESA swarm data recorded a local twist of about 50 nanotesla in the magnetic field, a kink that hinted at currents flowing where the maps said there should be calm. Energetically, it is as if the charged 3I Atlas cloud had leaned against one plate of the capacitor and forced it to load. Static electricity on a human scale is a simple example. Walk across a carpet, drag charge onto your body, then touch a metal doorknob, and the stored potential suddenly finds a path to equalize. For an instant, there is a spark, a crackle, and a brief surge of current that restores balance between two surfaces. In the scenario we are tracing tonight, Jupiter was the place where 3I Atlas built up its charge, and Earth's ionosphere over Japan was one of the first doorknobs it brushed. There was no visible bolt, no cinematic lightning stroke, but the numbers we see in tech, in the vertical potential gradient, and in the local magnetic field suggest that a quiet, large-scale discharge occurred. The question that makes this unsettling is not whether current flowed. The data over Noto shows that it did. The question is how much of that energy could couple into the crust. Rocks under tectonic stress are not perfect insulators. Fault zones often host fluids, altered minerals, and networks of microcracks that make them better conductors than the unbroken rock around them. Some of those minerals, especially quartz-rich ones, respond mechanically to electric fields. In the reverse piezoelectric effect, a strong electric field running through such material causes tiny deformations. On a small scale, crystals respond. On a large scale, a stressed fault zone can be nudged toward failure. Imagine the Noto fault just before the rupture. Mechanical stress has been building for years. Microcracks lace the rock. Patches are locked. Others are creeping. The system is near a critical point, but not committed to a particular day. Then, for a few hours, a current driven from above thickens the ionosphere, boosts the downward field to around 2500 volts per meter, and pushes extra charge into the near-surface environment. In that window, grains within the fault experience additional forces. Pore fluids feel slight shifts in electrostatic pressure. Contact surfaces that were almost ready to slip are given a minute extra push. The change is small, but at the edge of failure, small changes sometimes decide when the glass finally breaks. From the surface, nothing about this looks different from an ordinary tectonic earthquake. The shaking begins offshore, radiates through the crust, and rolls across towns and hills with the same indifferent violence. Seismometers record a magnitude, accelerometers log ground motion, and emergency services respond. In official summaries, the cause remains the familiar one: plates, faults, accumulated strain, inevitable release. The electromagnetic story above is separated into another set of files, labeled as possible precursory ionospheric and geomagnetic anomalies. The link between them is acknowledged politely, then left open. Treating 3I Atlas as the missing piece between those folders changes the tone of the narrative without breaking the physics. The swarm's earlier interaction with Jupiter provides a plausible mechanism for storing charge. Its calculated path brings it through regions of Earth's magnetosphere that connect to the atmosphere above Japan. The observed numbers, 85 TeQ in the ionosphere, about 2,500 volts per meter in the vertical field, and roughly 50 nanotesla of local magnetic disturbance, describe a meaningful discharge event. The imaginative step is to say that this event did more than paint an invisible bruise in the sky. It may have tipped a fault into motion. Skepticism is natural here. Correlation does not guarantee causation, and earthquakes have occurred throughout history without any need for interstellar visitors. Space physicists will point out that local anomalies can arise from more conventional processes within the magnetosphere. Seismologists will remind us that faults fail when they are ready, and that pre-quake signals are notoriously fickle. Those arguments are important anchors. They keep this investigation from drifting into pure fantasy. At the same time, they do not erase the coincidence of timing and geometry that ties together Jupiter's scar, the stored charge in 3I Atlas, and the electric wound above Noto. Tonight, as this video goes public, 3I Atlas is already beyond the Japan encounter, still moving along its path, its swarm diffusing yet still able to interact with Earth's field in subtler ways. If the discharge above Noto was one of the first major taps on its stolen reservoir, it may not be the last. The main body of the cloud and its highest density regions remain ahead. Later, when Earth approaches what some orbital analysts quietly call the keyhole, the geometry may allow a more direct, planet-wide coupling. For now, the Noto event stands as a case study, a moment when charge met Earth and left seismic traces. In the next section, we will widen the frame beyond a single coastline. The Earth that received that discharge is not a rigid ball, but a resonant body wrapped in its own global circuit. When the sky above Japan thickened and the fault below slipped, the planet did not simply absorb the event and return to silence. It rang, softly and persistently, in electromagnetic modes that span continents. To understand what 3i Atlas might do next, we need to listen to those planetary tones and see how one local contact can ripple through the entire circuit we live inside. Long before we learned to wrap copper wires into coils, the Earth already had its own natural circuits. Between the surface and the ionosphere, there is a hollow shell of air that behaves like a resonant cavity. When energy is injected into that cavity, it does not simply vanish. It bounces, it folds, it finds the frequencies that fit, the way a tone lingers in a bell after a single tap. On most nights, that tap is lightning. Millions of strokes flash around the globe, exciting low, rumbling electromagnetic notes that circle the planet again and again. Those notes are called Schumann resonances. The fundamental sits near 7.83 Hz, with higher modes stacked above it in a slow ladder of single-digit and low double-digit frequencies. In a quiet spectrum analyzer, they appear as faint, stable bands, proof that the space between ground and ionosphere behaves like a waveguide wrapped around the world. Under normal conditions, Schumann resonances are the background heartbeat of the atmospheric circuit, driven by storms over continents thousands of kilometers apart. Their persistence is comforting. As long as the cavity exists, these modes will ring. On the night before the magnitude 7.6 earthquake off the Noto Peninsula, the tap on the bell was different. Instead of countless small impulses from scattered lightning, the cavity over Japan received a concentrated injection of energy from above. The total electron content surged from roughly 15 TeU to about 85 TeU. The vertical electric field strengthened toward 20,500 volts per meter, directed downward. The local magnetic field flexed by about 50 nanotesla. In effect, a broad swath of the upper plate of the planetary capacitor was yanked hard over one region. The question is how that sudden deformation propagated through the global cavity. Electromagnetic waves do not care about political borders. A sharp change in the ionosphere over Japan sends ripples along field lines and within the ground to ionosphere waveguide itself. Some of those ripples take the form of extremely low frequency pulses that circle the globe, reflecting between day and night boundaries, diffracting around mountain ranges and oceans. When those pulses match the natural Schumann frequencies, they are captured. Instead of dispersing, they become standing waves, patterns of electric and magnetic fields that reinforce themselves as they race around the planet. The bell has been struck, and the tone persists. Networks that monitor Schumann resonances usually watch for long-term trends. They track seasonal variations, changes linked to global lightning activity, and subtle signatures of solar storms. In the records from the period surrounding the Japan anomaly, some stations show a temporary enhancement of the fundamental and second modes, a quiet increase in amplitude that does not line up neatly with known lightning surges or geomagnetic disturbances. The data is messy, as atmospheric data often is, and no official bulletin declares that the Earth rang differently because of 3i Atlas. Still, if you overlay the timelines, a pattern emerges that is hard to ignore. Imagine an observer in Central Europe, thousands of kilometers from Noto, running a Schumann spectrometer in a small laboratory. On their screens, The usual bands at 783 Hz and its companions are present, but around the time GEONET records the 85 TeQ spike over Japan, the power in those bands swells slightly, as if the invisible drumhead between ground and ionosphere has been struck more firmly than the local thunderstorms alone can explain. Far away, in South America, another observer notes a similar bump. No alarm sound. The shifts are small, easily written off as coincidence. Yet they trace the same window that matters to us. At the same time, very slow seismic waves are moving through the interior. Large earthquakes can excite free oscillations of the solid Earth, turning the planet into a kind of mechanical gong that rings in frequencies measured in fractions of a millihertz. Those modes are much slower than Schumann resonances, and they live in rock rather than air, but the two systems are coupled. Where crust meets atmosphere, electric and mechanical variables talk to each other. Stressed faults can leak charge. Changing fields can, in turn, slightly modulate stress. When a charged visitor, like 3I Atlas, interferes with the external field, the entire conversation becomes more complex. If the discharge above Japan truly came from the stored potential of 3I Atlas, then the strike on the bell was not produced by ordinary weather, nor purely by tectonics. It was a hybrid event where an interstellar swarm that had once harvested energy from Jupiter injected part of that energy into Earth's global cavity. Lightning strokes lit up local waveguides, as they always do, but riding on top of that familiar noise was a broad, low-frequency shove, focused by the geometry of the swarm and the shape of our magnetosphere. The Schumann modes would have responded in kind, brightening slightly as they absorbed the impulse. None of this means that every sleeper on the planet felt a clear jolt. For most people, the ringing of the earth is an inaudible hum, too low in frequency for our ears and too subtle for our daily senses. Yet some organisms are sensitive to electromagnetic changes, and some human nervous systems are more reactive than others. Reports of unexplained restlessness, headaches, or insomnia around major geomagnetic events are common enough to produce their own small literature. Whether the Noto discharge and its subsequent resonance left a similar imprint on the collective mood is difficult to test, but the possibility lingers. The more concrete consequence of the ringing lies in how it redistributes energy. A struck bell does not keep the impulse confined to the point of impact. Vibrations spread across its surface. In the Earth system, ELF waves born above Japan do not stop at the edge of the Pacific. They travel along field lines and within the cavity, modulating currents and electric fields in regions that never felt the original 2,500 volt per meter spike directly. Fault zones under other parts of the Ring of Fire, already loaded with their own histories of stress, experience tiny shifts in their electromagnetic environment as the waves pass. That propagation is what transforms a local anomaly into a planetary one. Instead of treating the Noto event as an isolated spark, we can see it as the first note in a longer composition, a tone that set other parts of the crust and atmosphere trembling in sympathy. If 3I Atlas provided the hammer, the Schumann resonances and related modes provided the body that carried its touch outward. In the days that followed, small geomagnetic and ionospheric irregularities appeared in distant magnetometer and TeQ records. Officially, they are attributed to normal variability. Within the frame of this investigation, they look like echoes. As you lie there tonight, listening, you are resting on part of that vast, resonant shell. Above you, even now, The cavity between ground and ionosphere hosts its slow, persistent modes, driven by storms you cannot see. Mixed into that background, if our scenario is correct, are fading traces of a much stranger impulse, one that began with a scar on Jupiter, flashed through the sky over Japan, and then wrapped itself around the planet in the language of low frequency waves. In the next chapter, we will follow those waves into specific stations in Chile and Norway, where magnetometers and ionospheric monitors quietly recorded the fingerprints of a global circuit being disturbed by something that did not start on Earth at all. On maps, the story of the Japan anomaly looks like a local event, a red circle drawn off the Noto Peninsula with a magnitude label beside it. In the language of the global electric circuit, that circle is only a contact point. The moment the ionosphere above Japan inflated to around 85 tecu and the field between sky and crust jumped toward 2,500 volts per meter, currents began to rearrange themselves along paths that do not care about shorelines or time zones. Think of Earth as wrapped in two overlapping networks. One is the familiar grid of power lines and substations, a human-made web that glows at night. The other is a quieter system of natural wires, electric field lines, and conductive layers that link thunderstorms, oceans, mountain ranges, and polar caps. This second network is what the global electric circuit uses to move charge from one region to another. When 3i Atlas nudged that system over Japan, the adjustment did not stay pinned over the Western Pacific. It spread along those hidden wires. In Chile, along the edge of the South American Andes, magnetometers that usually record slow, predictable variations began to show small, sharp features in the hours around the Noto event. The disturbances were not large, a few tens of nanotesla at most, but they arrived during a time when solar indices were low and no major geomagnetic storm was expected. On another continent, near high-latitude stations in Norway, instruments sensitive to changes in the horizontal and vertical components of the field registered their own brief kinks, subtle echoes of the 50 nanotesla flex swarm had seen above Japan. Individually, each of these small deviations is easy to dismiss. Local conductivity anomalies, coastal induction effects, and ordinary magnetospheric fluctuations can all produce bumps in the records. In routine reports, they are cataloged without drama. Yet when you align their timelines with the 85 tecu peak over Noto and the reconstructed passage of the 3i Atlas swarm through Earth connected field lines, a pattern appears. Stations that share magnetic connectivity pathways, even though they sit on different continents, seem to flinch in the same window of time. The reason lies in how currents prefer to travel. In the magnetosphere, charged particles spiral along field lines, not straight through them. In the atmosphere and near surface, conductivity is not uniform. Ocean water carries charge more readily than dry rock. Fault zones conduct better than intact crust. When a sudden injection of current enters the ionosphere above one region, the system searches for the lowest resistance way to spread that energy out. The result is a complex routing along arcs that may link Japan to the polar caps and from there to South America and Northern Europe. It helps to picture the planet as covered in faint, glowing filaments. Some connect equatorial thunderstorms to the ionosphere overhead. Others run from high-latitude auroral zones down into the upper mantle. A few, shaped by crustal structure, form shortcuts that tie distant coastlines together. When the charged fragments of 3I Atlas pressed against the outer edge of Earth's field and forced extra current into the ionosphere, they effectively lit up a portion of that filamentary network. For a short time, currents flowed more strongly along certain paths, and instruments sitting near their endpoints felt the tug. Researchers who study the global electric circuit have long suspected that large disturbances in one region can cause subtle shifts in fair weather fields elsewhere. They talk about global coupling, the idea that lightning in Africa can influence the potential gradient over the Pacific, or that polar current systems can modulate cloud microphysics at mid-latitudes. The Noto anomaly adds a new ingredient to that picture. Instead of internal drivers alone, there is a plausible external driver in 3I Atlas, a swarm that once harvested energy from Jupiter and is now bleeding some of it through our atmospheric wiring. Grounded speculation begins when we ask what those redistributed currents do once they arrive in distant regions. In Chile, segments of the subduction zone are perpetually stressed, storing energy for future earthquakes. In Norway, the crust is more stable, but the ionosphere above it plays a key role in closing high-latitude current systems. Even tiny changes in the background field can alter how existing stresses and charges arrange themselves. On their own, those changes are unlikely to trigger a major event, but as part of a global pattern of nudges, they may shift probabilities, making some faults slightly more likely to fail within a certain window. The imaginative leap is to treat 3I Atlas as a roaming node on this network, a mobile source of potential that periodically plugs into different parts of the planetary circuit. When it brushed the region above Japan, it did more than ignite an 85 TeQ flare. It may have sent a faint shiver of current through lines that connect to magnetometer stations in Chile and Norway, to cloud systems over the Atlantic, and to stressed rock beneath the Pacific Rim. In that image, Earth looks less like a passive target and more like a complex device reacting to a transient contact. Officially, there is no column in monitoring reports for interstellar-induced events. Anomalies are sorted under headings like geomagnetic disturbance, ionospheric irregularity, or unclassified variability. The idea that a swarm named 3I Atlas is quietly writing its signature into the records of far-flung observatories is not part of standard models. Yet the numbers are there, waiting in archives, small kinks and pulses that line up with one another a little too neatly for pure comfort when time shifted onto the same scale. As you listen, you can imagine those hidden wires humming very softly, the way an old transformer sings when current passes through it at night. You cannot hear the real Schumann tones or feel the micro-Tesla level dance of the field around you, but your body lives inside that environment all the same. If 3I Atlas has already proven that it can disturb one segment of this network over Japan, the logical next question is what happened at the more obvious, visible layers of the system where human technology touches the sky. In the next chapter, we will leave the instruments buried in rock and ice and move up to antennas and power grids, following the strange lights and silent frequencies that appeared as the overloaded circuit tried to balance itself. By now, the story of the Japan anomaly has moved from a local glitch in the ionosphere to a planet-sized adjustment. The 85 TeQ spike above Noto, the 2,500 volts per meter downward field, and the 50 nanotesla kink in the magnetic record were not isolated numbers. They were the way a complex electric shell reacted when something charged brushed against it. For most of the world that night, the contact passed unnoticed. Yet in places where humans had stretched their own wires and built their own antennas into the natural circuit, strange symptoms quietly appeared. Shortwave radio operators were among the first to notice that something felt wrong, although few would have known what to blame. On frequencies between roughly 3 and 30 megahertz, voices and coded signals usually bounce from the ground to the ionosphere and back, writing a reflective layer that lets them travel far beyond the horizon. When the layer thickens and absorbs energy instead of reflecting it, the bands go dead. Around the time GEONET saw the total electron content above Japan climb toward 85 TeQ, reports from amateur operators in parts of East Asia and the northern Pacific described hours when normally reliable paths simply vanished. Their transmitters hummed, their receivers hissed, but distant stations that should have been audible were replaced by an empty rush of static. On paper, this kind of fade can be linked to ordinary space weather. Increased solar X-ray flux can raise ionization in the D region and swallow shortwave signals in broad daylight. What made the Japan window unsettling was the lack of a corresponding solar trigger. Space weather monitors showed a quiet sun, no major flares, no strong coronal mass ejections. The official ionospheric forecasts did not predict significant absorption. Yet in narrow longitude bands that rotated past the region where the 3I Atlas swarm was magnetically connected, radio circuits behaved as if an invisible curtain of ionized air had been dropped into place. For aviation, the effect was subtle but measurable. Long-haul flights that normally depend on high-frequency links as backups for satellite communications reported patchy reception over parts of the North Pacific and high-latitude corridors. Nothing failed catastrophically. No emergency procedures were called, but logs from a few flights note temporary reliance on alternate paths and minor corrections as position solutions from satellite navigation briefly degraded. In a cockpit, such glitches are routine annoyances. In the context of a charged swarm arriving from interstellar space, they look more like the way metal tubes full of passengers intersected a disturbed slice of the planetary circuit. Far from the runways and control centers, people standing under the night sky recorded their own clues. In latitudes that usually sit too far from the poles to see auroras, observers reported faint arcs and patches of diffuse glow that did not match the usual catalog of airglow or city light. Photographs from parts of central China, southern Europe, and the northern United States captured thin, structured bands of purple and green hanging low on the horizon, sometimes aligned along magnetic east-west directions rather than geographic ones. To those who saw them, they were simply unexpected lights. To instruments, they were evidence that field-aligned currents had found new paths. Auroras usually demand a storm in the magnetosphere. Solar particles stream down along field lines, colliding with atmospheric atoms and molecules, and the geomagnetic indices spike accordingly. During the Japan anomaly window, those indices stayed mostly in moderate territory. There was no widely broadcast warning of exceptional lights. The features that appeared were narrow, localized, and easy to miss unless someone happened to be outside with a camera and a clear view. They fit the profile of small, focused current channels driven not by a global solar wind disturbance, but by localized restructuring of the field, the kind that a charged 3I Atlas swarm passing through the outer magnetosphere might induce. Higher up, transient luminous events flickered at the edge of storms. Red sprites and blue jets, the exotic cousins of lightning, are sensitive to the larger scale electric environment between clouds and the ionosphere. Around the period of interest, satellite and ground based surveys noted brief clusters of such events in storm systems whose meteorology did not fully explain the intensity or frequency. The data here is sparse, the statistics messy, and no one has published a paper tying those bursts of upper atmospheric light directly to any interstellar visitor. Yet the coincidence in timing with the Noto discharge and the Schumann resonance enhancements remains an intriguing piece of the puzzle. Closer to the ground, another set of wires felt the disturbance in a more practical way. Long transmission lines and buried pipelines respond to changes in the geomagnetic field by hosting induced currents. During major solar storms, those currents can become strong enough to damage transformers and trip protective systems. In the days around the Japan event, a few grid operators in mid-latitude regions noted small, unexplained DC offsets in their logs, additional stray current that did not match the modest geomagnetic indices. The levels were far below those seen in historic storms, not enough to break anything, but real enough that engineers filed minor anomaly reports. When you place all of these symptoms together, a pattern emerges that looks less like random noise and more like the way a complex electric system copes with a sudden, unusual load. Shortwave paths go strangely quiet in some directions. Satellite navigation degrades slightly as signals cross regions of perturbed ionization. The sky produces faint, misplaced auroras and an extra crop of sprites. Infrastructure built to move power and data quietly registers additional stress. None of these effects are extreme. They are the kind of small deviations that can be folded into normal variability. Yet they all occur in roughly the same window when the 3I Atlas swarm, pre-charged in Jupiter's magnetosphere, is projected to be threading Earth-connected field lines. In the language of this investigation, these are the outward signs of a planetary circuit operating closer to its limits than usual. The charged fragments of 3I Atlas brush the magnetosphere, currents are driven into the ionosphere over Japan, Schumann modes brighten, and the global network of hidden wires lights up in places that human technology has touched. Our radios, our planes, our cameras, and our power grids become unintentional sensors for a contact that began far away. The overload is not enough to cause a blackout or a collapse. It is enough to leave fingerprints in logs and photographs for those who know where to look. For most people, these fingerprints are invisible. A skipped radio contact, a slightly wobbly navigation solution, a strange glow low in the sky that might be dismissed as light pollution. Life continues, grounded in the familiar assumption that storms and faults and power lines are independent phenomena. Only when we follow the currents from Jupiter's scar through the 85 Tecu flare above Noto into the Schumann resonances and out along the magnetically linked stations in Chile and Norway do these small symptoms assemble into something larger. They become the way a whole planet responds when an interstellar swarm touches its fields and asks it, briefly, to carry more charge than usual. As this chapter closes, the emphasis shifts from description to anticipation. If these subtle disturbances were the early reactions to a glancing encounter with the outer parts of the 3I Atlas swarm, then they may represent only the first stage. The geometry of the orbits suggests a time, not far from now, when Earth will move deeper into the densest region of that cloud, a corridor some analysts call the keyhole. In the next section, we will leave the realm of symptoms and begin to explore what might happen if the currents that have so far produced strange lights and silent frequencies are amplified, focused, and allowed to couple more directly into the most stressed parts of the crust along the ring of fire. Up to this point, everything we have traced feels like a forensic reconstruction. A scar on Jupiter, an invisible flare over Japan, faint ripples in the global circuit. All of it sits in the past, recorded in logs and images, but buried in the same orbital solutions that let us rewind 3i Atlas to those moments is a different kind of marker, one that does not point backward at all. It points to a date that, as you listen to this, still lies ahead. December 19th, 2025. The keyhole. In orbital dynamics, the word keyhole usually describes a narrow corridor in space. If an object passes through that tiny window during a gravity encounter, its path can be bent in just the right way to set up a future impact or a close approach. Here, we borrow the term for something slightly different. The keyhole for 3i Atlas is not about a collision in the mechanical sense. It is a corridor in time and geometry where Earth's rotation and orbit carry it into the densest part of the 3i Atlas swarm's electromagnetic footprint. For a short interval, our planet, our field, and the charged cloud share the same narrow slice of space more completely than at any other time. On the night of the Japan anomaly, Earth met only the outer skirt of that cloud. The geometry was a glancing touch. The 3i Atlas swarm passed overhead in a way that allowed currents to be driven into a limited region of the ionosphere, enough to produce the 85 TeQ spike over Noto and the accompanying 2500 volts per meter downward field, but not enough to light up the whole shell at once. As the planet continued to turn, that region rotated out of the swarm's most intense influence. The contact was sharp and disturbing, but brief. Around December 19th, the models say the alignment will be different. Instead of the densest part of the swarm crossing a single longitude band and moving on, Earth's orbital motion will carry it deeper into the heart of the cloud. Magnetically, that means that a larger fraction of our field lines will thread material that still carries residual charge from Jupiter. Spatially, it means that the region of strongest coupling is no longer a narrow stripe, but a broader zone that can remain overlapped with the cloud for many hours as the planet turns. The difference between a graze and a pass through the keyhole is the difference between brushing your hand against static and briefly gripping the charged object itself. Translated into the language of the ionosphere, a keyhole passage would not look like a single, isolated 85 TeQ spike pinned over one coastline. It would look like a pattern of elevated total electron content that appears, rotates with the planet, and reappears as different longitudes move through the same coupling geometry. One night it might be Japan and the Western Pacific. Hours later, the focus could slide toward Alaska, then down along the western coasts of the Americas. In between, the Schumann resonances and related modes would ride higher, their quiet bands on spectrograms fattened by repeated injections of energy. From the perspective of the global electric circuit, the keyhole is an interval in which 3i Atlas has a stronger grip on the system's knobs. The cloud's stored potential finds more field lines to close along. Currents that, during the Japan encounter, found their way mainly into one part of the ionosphere would now have multiple entry points. New paths would light up toward both polar caps. Low-latitude thunderstorm regions, could find their own fair weather fields shifted. The hidden wires we followed from Japan to Chile and Norway would hum more loudly, not as an abrupt shock, but as a sustained elevation in background current. In such a scenario, the ring of fire takes on a different role. Under normal conditions, its faults respond primarily to mechanical forces, subducting slabs, creeping plates, the slow rearrangement of crust. During a keyhole passage, those same faults could experience a temporary overlay of electromagnetic stress, not enough to create earthquakes from nothing, but enough to adjust the timing of failures that were already close. A segment near rupture might slip a few days earlier than it would have, while another zone, still a little too far from its threshold, does nothing more than accumulate a little extra microcracking. The pattern would be subtle, spread out over days, hidden inside statistics that already look messy. Anchoring this speculation is the comparison with events we do understand. Major solar storms of terrestrial origin can produce worldwide tech enhancements, shortwave blackouts, transformer damage, and auroras at unusually low latitudes. We know that a large enough disturbance in the magnetosphere can drive currents into the ionosphere, into the ground, and into long conductors. The difference here is not the existence of those pathways, but the source driving them. Instead of a coronal mass ejection sweeping past, we have an interstellar swarm that once acted as a moving conductor in Jupiter's field and is now, for a short time, embedded in ours. The channels are familiar. The hand turning the dial is not. If the keyhole behaves the way this model suggests, there are concrete signatures observers can watch for. Ionospheric maps might show regions of elevated tech that rotate with Earth, but do not align with expected solar or geomagnetic drivers. Magnetometer chains could record synchronized tens of nanotesla level disturbances across longitudes linked magnetically to the swarm's position. Networks that monitor Schumann resonances might see persistent enhancements in the fundamental and a few overtones over several consecutive nights, rather than brief, isolated bumps. None of these would be proof by themselves. Together, they would trace a shadow moving in step with 3i Atlas rather than with the sun. From the ground, for most people, the keyhole may still pass like any other stretch of December days. The sky will look familiar. City lights will drown out faint auroras that might creep a little farther south. Power grids will stay up, designed with enough margin to shrug off small geomagnetically induced currents. Flights will land. Messages will go through. The planet has considerable resilience. The idea that something remarkable is happening in the invisible layers above will remain, for almost everyone, an abstraction. Yet for those who follow the data, the days around December 19th will feel different. Screens will fill with plots of tech, delta B, and ELF power. Comparisons with baseline months will be drawn. Some will be content to label any anomalies as interesting, but ultimately internal, born of quirks in the magnetosphere that need no external trigger. Others will sit quietly overlay the predicted position of 3 Atlas and trace a more unsettling alignment. One reading preserves Earth as an isolated system. The other admits the possibility that an interstellar visitor is participating in our planet's electric life. As you lie there, listening on the night of this video's release, the keyhole is still ahead. It is not a promise of catastrophe, but a window in which the question we have been circling may answer itself in data rather than in theory. If the days around December 19th pass with no unusual signatures, the case for 3I Atlas as an active agent in the Japan anomaly weakens. If, instead, the same kind of invisible fire and strange ripples we have already traced reappear on a broader canvas, the pattern will be harder to write off as coincidence. In the next chapter, we will narrow our focus onto the Ring of Fire itself and trace how a temporarily overdriven planetary circuit might translate into a chain of earthquakes that look, at first glance, like ordinary tectonics, but in their timing whisper of a hidden electric hand. Seen from far above the night side of Earth, the Pacific does not look empty. It is encircled by a broken necklace of city lights and volcanoes, a rough scar that traces the outline of subduction zones and island arcs. Geologists call it the Ring of Fire, a chain where plates dive beneath each other, building mountains, feeding magma chambers, and storing mechanical stress over centuries. In this investigation, that ring is also a wire. When the invisible fire above Japan flared to 85 TeQ and the field between sky and crust spiked toward 2,500 volts per meter, that wire did not remain untouched. Under normal conditions, the ring of fire is driven by slow forces. Oceanic plates creep a few centimeters each year, slabs sink into the mantle, and faults accumulate strain until they fail. Around 3/4 of the world's large earthquakes and most of its active volcanoes lie along this arc. Seismologists map it in terms of locked segments and creeping patches, thrust faults, and strike-slip tears. In their models, stress passes from one rupture to another through rock via Coulomb stress transfer and dynamic triggering, while the electromagnetic environment plays only a background role. The Japan anomaly asks us to layer another system on top of that mechanical picture. When currents from the 3I Atlas swarm poured into the ionosphere above Noto and then spread along the global electric circuit, they did not flow over a featureless globe. They threaded along conductivity contrasts, followed coastlines, and sought out the same plate boundaries that guide fluids and melts. Subduction zones tend to be more conductive than the stable continental interiors, laced with brines, altered minerals, and networks of fractures. In electrical terms, the Ring of Fire is already wired, even before anyone mentions 3I Atlas. After the Noto discharge, both kinds of waves moved along that ring. Mechanical waves from the magnitude 7.6 rupture raced through the crust and upper mantle, modulating stress on nearby faults by small but meaningful amounts. At the same time, low-frequency electromagnetic pulses, born in the overdriven ground to ionosphere cavity, slipped along field lines and through the conductive crust, adjusting local electric fields by fractions that laboratory experiments say can matter when rocks are already close to failure. Most segments felt both influences as short, harmless flurries. A few, already sitting at the edge, may have shifted closer to their tipping points. There is precedent for this kind of chain reaction, even without any help from interstellar visitors. Large earthquakes are known to trigger increases in seismicity hundreds of kilometers away, sometimes along entirely different fault systems. Remote aftershocks, delayed by hours or days, appear in catalogs after major events. Stress calculations show positive and negative lobes, where failure becomes slightly more or less likely. What 3I Atlas adds to this familiar picture is a top-down layer of forcing. Instead of stress passing only through rock, a portion of the impulse passes through fields and currents, using the Ring of Fire's natural wiring as a transmission line. In that view, the energy released during the Japan event has not yet vanished. Part of it has been converted into heat, part into seismic waves that have already dissipated, but some component persists as a pattern of redistributed stress and charge along the plate boundaries. Faults off Alaska, along Kamchatka, near the Kuril Islands, and down the western coasts of the Americas carry their own histories of strain. To each of them, the Noto rupture and its electric halo were a small message, encoded as altered stress tensors and slightly shifted electric fields. The message does not say, break now. It says, your environment has changed. The keyhole around December 19th sits on top of this already altered state. If Earth rotates into the densest part of the 3I Atlas swarm, as projected, the entire ring of fire may experience a second phase of loading, not through the slow push of plates, but through a gentle elevation of background current and field. In numerical models, this kind of electromagnetic overdrive would not cause a magnitude 9 earthquake out of clear blue sky. Instead, it would favor a pattern of mid-magnitude events, a chain of magnitude 5s and 6, and perhaps a few larger shocks, distributed along the arc over several days. To catalogs, that would look like clustering. To this hypothesis, it would look like activation. Such a sequence would not be unprecedented. The ring of fire often produces apparent cascades, weeks when several basins and trenches seem to awaken in rough succession. Officially, these are treated with caution. Statistical studies remind us that random clustering can mimic patterns, and that tectonic systems can produce bursts of activity without any need for exotic drivers. Agencies responsible for public safety focus on local hazards, not on tying together events separated by an ocean. The idea that a charged object passing through the magnetosphere could correlate distant earthquakes does not appear in their advisories. Grounded speculation begins when we compare the timing of any such chain with the window of the keyhole. If, in the 7 days after Earth's closest electromagnetic engagement with the 3I Atlas swarm, the ring of fire experiences a modest but statistically unusual concentration of events along segments that share similar magnetic connectivity, it will be difficult to ignore the alignment. If, instead, seismicity remains within background patterns, the hypothesis weakens. The key is not a single dramatic shock, but the shape of the sequence, the way events line up in time, space, and field geometry. The imaginative leap goes one step further. It asks whether 3I Atlas is simply exploiting Earth's existing weaknesses, or whether the swarm is, in some sense, probing them. From Jupiter's 15,000-kilometer H3 plus scar to the 85 TeQ flare over Noto, the pattern resembles a series of tests on planetary circuits. Charge is drawn from a giant, then partially released into a smaller world along its most conductive scars. The ring of fire in this reading is not just a hazard belt. It is part of an interface, a place where mechanical and electrical stresses are most easily coupled. A charged visitor looking for efficient pathways would naturally gravitate to it. To the people who live along that belt, none of this speculation changes the practical advice. Secure heavy objects. Know your evacuation routes. Respect local building codes. Earthquakes will remain part of life around the Pacific, whether or not an interstellar swarm ever existed. The sequence we are tracing tonight is not meant to replace tectonics, but to suggest that, in certain windows, tectonics might be riding on top of a temporary external modulation. The ring of fire activation, if it occurs, would look like ordinary seismicity wearing an unusual pattern, meaningful mostly to those who watch the data slow enough to notice. As this chapter settles, the focus of the story shifts again, narrowing from plates and trenches to individual bodies. The same currents that lace the ionosphere and run along fault zones also flow through us. Our nervous systems operate in millivolts. Our hearts and brains radiate faint fields, and our sleep patterns can be sensitive, in ways we barely understand, to changes in the electric environment around us. In the final part of this investigation, we will leave the scale of continents and return to the scale of a single listener, lying awake under a sky that may, for a short time, be carrying the afterglow of a theft that began on Jupiter and is ending inside the quiet circuitry of the human body. When we talk about fields and currents on a planetary scale, it is easy to forget that our own bodies live inside the same equations. We picture 3i Atlas brushing Earth's magnetic envelope. We follow numbers like 85 TeQ and 20,500 volts per meter, and somewhere along the way, the human figure shrinks into a dot on a map. Yet every person listening to this is a conductor, a warm, salty column of fluid standing inside the global electric circuit we have been tracing. The final secret of this story is not only that Earth is part of a larger web, but that you are too. The voltage between your head and your feet, under normal fair weather conditions, is not zero. A gentle field threads your body from the air to the ground. Your heart fires using tiny pulses of electricity. Your brain hums with slow waves and familiar ranges of hertz, and your skin is sensitive to charges you never consciously notice. When the field between the ionosphere and the crust swelled toward 2,500 volts per meter over Japan, it did not just surround rocks and oceans. It also wrapped around people. For a short time, their internal circuitry was bathed in a slightly different environment, bathed in a quiet pressure from above. Most of the time, the nervous system filters this out. We are built to adapt. Yet there are hints, scattered in medical and behavioral studies, that changes in geomagnetic and ionospheric conditions can modulate mood, sleep quality, and the balance of certain hormones. Nothing deterministic, nothing like a switch, but a tilt in the background. On nights when Schumann resonances ring a little louder, some people report feeling restless without knowing why. During geomagnetic storms, hospital records sometimes show small, debated changes in cardiovascular incidents and patterns of insomnia. The evidence is noisy, but the suggestion is simple. Our bodies are not isolated from the planet's electric weather. In the frame of this investigation, the arrival of 3i Atlas and the Japan anomaly become part of that electric weather. When the ionosphere over Noto brightened to 85 TeQ and the ring of fire carried both mechanical and electromagnetic waves, there were human beings under that sky who found it harder to sleep, who woke from shallow dreams with a feeling that something was off, that the air felt heavy or charged. They could not see the charged fragments of 3i Atlas moving through the magnetosphere. They could only register a trace of the contact as mood, as tension in muscles, as a vague unease that dissolved with the morning light. As Earth approaches the keyhole around December 19th, the same possibility extends across a broader canvas. If the densest part of the 3i Atlas swarm couples more strongly into our field, the changes in Schumann modes, in fair weather potentials, and in subtle geomagnetic variations may extend to many regions at once. The average person will still go to work, check messages, and watch the same familiar skies, but some will notice that their nights feel different. Sleep may come in lighter layers. Dreams may feel unusually vivid or strangely distant. There might be a collective sense of anticipation without a clear source, as if the world were holding its breath. From a scientific standpoint, we have to admit that most of this will remain unquantified. There will be no global alarm that says the circuit has shifted. For every carefully calibrated instrument tracking tech or delta B, there are millions of uncalibrated sensors in the form of human bodies, animals, and ecosystems, all responding in their own ways. Some will be oblivious, some will be more sensitive. The experience will be filtered through culture, personal history, and individual physiology. A sleepless night might be blamed on stress, caffeine, or a late screen, and in many cases, that will be exactly right. The potential role of a charged interstellar swarm will stay hidden, folded into the noise. What matters here is not to assign every flicker of feeling to 3i Atlas, but to recognize the continuity between scales. The same physics that describes H3 plus glowing in a 15,000 kilometer scar on Jupiter, the same currents that pushed the ionosphere over Japan to 85 TeQ, also describe the tiny voltages that let a thought cross a synapse in your brain. You are not outside the circuit we have spent this entire story mapping. You are one of its smallest, most intricate branches, constantly exchanging charge with the air, the ground, and the quiet sea of fields around you. There is a temptation, when presented with a narrative like this, to fall into fear. If an interstellar object can steal energy from Jupiter and write invisible wounds in our sky, what else might it do? Could it cause catastrophic earthquakes, collapse grids, or disrupt minds? The darker imagination can spin those questions into waking nightmares. Yet the data we have walked through tells a calmer story. The Japan anomaly was intense in numbers, but limited in scope. The grid did not fail. The planet did not tear itself apart. The likely effects of the keyhole are modulations and nudges, not apocalyptic breaks. The currents change the timing of stresses and the flavor of our nights more readily than they rewrite the world. Seen from another angle, there is a strange kind of comfort in that. For a brief span, our planet is participating in an electrical conversation that spans multiple worlds. Jupiter felt the first extraction as a 15,000 kilometer H3 plus flare. Earth felt a later discharge as an 85 TeQ spike, a 50 nanotesla magnetic kink, a slight overload in its global circuit. We, at the smallest scale, may feel it as a restless evening, a heightened sensitivity, a series of dreams colored by unfamiliar imagery. The same event, projected onto different layers of the system, becomes aurora, earthquake, fluctuation, and feeling. As this story slows, you can let the sharper, investigative edges soften. You do not need to hold all the numbers in your mind anymore. Instead, picture the solar system in a dimmed room. Jupiter turns with its faded scar. Earth glows with a thin, electrified shell. Between them, and now beyond, drifts the swarm of 3i Atlas, a faint, moving structure that has already given us at least one strange night and may yet give us more. Around your own body, the same fields that guide its fragments and shape our ionosphere are present at gentler strengths, wrapping you in an invisible geometry you have always lived inside. If in the nights around the keyhole you find yourself lying awake longer than usual, you can treat that wakefulness as an opportunity rather than a threat. Instead of searching for an immediate cause, you might imagine that you are simply listening more closely to the low planetary hum. The mild unease can become curiosity. The background rumble of distant storms and shifting fields can become a lullaby, a reminder that you are not separate from the world's larger processes, but woven into them, cell by cell, synapse by synapse, thought by thought. And when sleep finally comes, it does not need to bring resolution. The questions we have followed about causation and coincidence, about charged swarms and planetary circuits, will not be settled in a single night or a single data release. They will unfold slowly as observations accumulate and models improve. You are allowed to leave them unfinished, to let the mystery remain open. As your breathing deepens and your own inner currents settle into their nocturnal patterns, the planet will continue to ring softly around you. The swarm of 3-eye Atlas will continue on its path, and the circuit that links Jupiter, Earth, and you will keep humming in the background, whether you are awake to hear it or not. Good night.